Okay, hi everyone. So we're very happy today to have Lukas Müller from the Perimeter Institute for Theoretical Physics in Canada, who is going to tell us about deformation, quantization, and categorical factorization homology. Lukas, please.
Yeah, okay, let me start by thanking the organizers for the invitation and everyone else for coming. So what I'm going to talk about is joint work with Eileen Carson, Karina Keller, and Jan Pullman, and it's still work in progress. So there are a lot of things which are not completely worked out, and some of the statements should probably be more likely understood as a expectation and not really as a proven statement yet. But some other things are in quite a good shape. So here's a really brief outline for my talk. I will start with some motivation coming from the type of structure one finds for point defects in perturbative quantum field theories, then discuss why the structure is not sufficient to capture interesting examples, namely coming from Chern-Simons theory or moduli spaces of flat bundles on surfaces. And then the main part of the talk, or the things which correspond to our work, will be about a categorification of the story. And yeah, so I will then introduce some factorization homology in a bit more detail. I'm not assuming that you know what it is. And I will also, in the last section, explain the main computational tool we use in terms of like an enriched version of scan theory. And then if there's time, I will mention some other applications our framework might be useful for. And I should also say, like, everything I'm going to say in the motivational bit will be slightly simplified, and some of the statements are somehow on a technical level not exactly correct in the way I state them. There need to be some additional words and technical details, which I just going to ignore. So for this, you should look at the references I point out. So let me start with the structure one finds for point observables in a quantum field theory. And for this, we start with some classical field theory which is given by fixing a space-time manifold M, which usually is equipped with some type of geometric structure, for example, a metric, or a spin structure, an orientation, or something similar. And the easiest example, the most common example in physics, probably just four-dimensional Euclidean space. And then there's a collection of classical fields, which are described by some type of sheaf on the opens, let's say for the moment with values in chain complexes, but also fields can also have more general structures, such as maps to a curved target space or something else. And a simple example to keep in mind are like smooth functions on an open subset. And then the dynamics of the theory is given by a local action functional, which is a map from the compactly supported fields to the real numbers. And for example, this is something like an integral or a free scalar field theory you see here. And now the classical physics is described by the solutions to the Euler-Lagrange equation. So they are given, they describe extrema of the action functional. So in a more formal way, one can also describe them as zeros of the differential of the action functional. And now, assuming that everything makes sense, I'm saying as well, then the action function actually gives a section of the cotangent bundle. There's also the zero section, and the space of solutions. Statistical solutions is just the intersection of these two subsets of the cotangent bundle, which is also a pullback, or which is a pullback defined as pullback. And then the classical things we can observe in a system are just functions on the space of solutions. Here's an example. If I have a field, for example, a scalar where I can measure its value at a point x0, or if I have a field and some test function, just as some function f, ensuring that this integral is compactly supported, I can measure something like the square of the second derivative of the field integrated. And now you can ask, like, what type of structure these observables have, and how can we find an axiomatic description of them? And for this, let me just start by observing that if I have three open subsets U1, U2, and U3 sitting in a bigger open subset W of M, then for this I get a map from the observables on U, tensor observables on U2 and U3 into observables in W, which is just given by measuring the things simultaneously and multiplying. And we denote these maps by M U1, U2, U3 into W. And they satisfy the following associativity condition. If I take two open sets and I embed them into a larger open set, and then take this larger set and U3 and embed them into W. So that's what's happening here. Then this is the same as first embedding into W2 and then into W. This is in a certain sense an associativity condition and an assignment of, let's say, chain complexes for the moment to any open of a manifold together with maps of this type. This is what's called a pre-factorization algebra. And now the main statement in the work of Costello and Graham is that when you work in a formal neighborhood, so you fix one solution and look at the formal neighborhood of it in the space of solutions, which on the physics side corresponds to doing like perturbation theory or using the classical BV formalism, then this pre-factorization algebra is actually a factorization algebra, and it takes values in what's called a P0 algebra. So a factorization algebra is just a pre-factorization algebra plus some locality condition, which is descent for so-called Rice covers, which are not going to be that important for what follows. If you want to know what they are, you can ask now or at the end, but otherwise I would just skip this. And then the other thing showing up here is the P0 algebra. These are generalizations of Poisson algebra. So Pn algebra is a commutative differential graded algebra A. And then it has a degree 1 minus n Poisson bracket, which goes from A tensor, which is just a Poisson bracket which is shifted. And for n equals 1, these reproduce ordinary Poisson algebras. And here's like an informal reason why you would expect to have such a Poisson, such a P0 structure on the space of solutions, namely, so these things, both things are graphs of functions in the cotangent bundle. So they're Lagrangian with respect to the standard symplectic form. And then if you are taking this intersection in an appropriate derived setting, then it should be -1, or like a derived intersection of Lagrangians is -1 shifted symplectic, and this then induces a P0 Poisson structure on the observer. This is also an incarnation of other things of like symplectic pairings one finds in physics, and like in the L infinity formalism, it's corresponded to having like a cyclic pairing. Okay, and now when we pass to the quantum observables of the theory, then they actually form a deformation of this P0 factorization algebra into a factorization algebra, which now takes values in chain complexes, which have a formal parameter, which are power series in a formal parameter h bar. And then if I take h bar to be 0, I reproduce in a certain sense the P0 structure on the classical observables. And now in many physical situations, and also later on in this talk, we will only be interested in spacetimes which look like a Cauchy surface or a hypersurface times the time direction. This, for example, is always true if the manifold is globally hyperbolic. So we want to understand factorization algebras on a cylinder like this, and there's a additivity statement for factorization algebras, which tells us that if I look at factorization algebras on a product with values in some target C, then this is a factorization algebra on sigma with values now in factorization algebras on T with values in C. And in addition, we will now assume that the observables are locally constant in the time direction. This is closely related to the condition that when in the physics is that if you can somehow, if you know your theory on a time slice, then uniqueness of time evolution should fix the theory completely. This is, as far as I can see it, it's not exactly the same, because here somehow also these smaller opens, there's some, like also for smaller things in space, there will be local constancy, but this assumption will make certain things easier, and furthermore, later on, everything will be locally constant anyway. So I will do this assumption for the moment, and then, so here we want to understand now locally constant factorization algebras on R1, and they are equivalent to associative algebras. And let me just briefly sketch of what this means. So to an open interval, we assign some vector space A or some chain complex A. And to all open intervals, we will assign the same one, because they all are homotopy equivalent, and locally constant exactly means that homotopy equivalent embedding are going to be mapped to weak equivalences. So they are all weak equivalent. And then we find the multiplication by looking at this map M U1, U2 for the embedding of these two red intervals into the black one, which gives us a map from A tensor A into A. And then the associativity condition will tell us that we find something like an associative algebra. Okay. So now we have reduced the problem we want to look at factorization algebras on sigma with values in associative algebras in P0 algebras. And now we, okay, that's weird. Now we also, you can use another statement which tells us that associative algebras and P0 algebras are actually P1 algebras. So in this setting, you read now on a time slice, we find a factorization algebra which takes values in normal Poisson algebras, which might be more familiar from like a phase space formulation of a field theory. And then let me just say that it's not completely clear how this is compatible with quantization. So we have seen that the quantum observables give me quantization of this P0 algebra structure. And now if I assume that the quantization is also locally constant in the time direction, I can equivalently describe this by some factorization algebra in Poisson algebras. And here we get some factorization algebra in associative algebras in a formal, with an informal power series. And then there one can take a H bar limit. H bar goes to 0 limit on both sides, and might naively expect this to commute, so that since this is a quantization, this should also be a quantization. However, this needs and would also imply what's known as BD additivity, which is a statement for which there's no formal proof. So there's some, this is slightly more involved than you might expect. Yeah. So are there questions up to now?
Sorry, I might have missed it. What's BD?
BD?
Valence
and Greenfeld, yeah. Like I didn't explain what it is, but it's like Valence and Greenfeld algebras. So they are the object P(n) algebra wants to deform into. So it's somehow some type of En algebra plus over H bar plus the condition that if you set H bar to be 0, you recover the Pn structure.
Sure, thank you.
Yeah, I didn't. Thanks for the question. Okay, and now, so we have seen that somehow functions on the space of solutions form a factorization algebra. But in the perturbative setting, so you can now ask, like, does this extend to the non-perturbative world or to other settings, maybe at least perturbatively, but maybe not just around one stochastic solution, but yeah, like a family of those. So, and like my go-to example, if I want to see what happens in a non-perturbative setting, are so-called Dijkgraaf-Witten series, because they have essentially no perturbative feature whatsoever. and they are completely non-perturbative, but they are also easy to handle because path integrals turn out to be finite dimensional. So for this, they are just gauge series fixed on a finite, built on a finite group G. So we fix some finite group G, and then the space of solutions in Dirac-Witten series is just the stack of G bundles on M. And this is now not a vector space. This is like a proper stack or a groupoid. I mean, the discrete Lie groupoid. The objects are principal bundles on M, and the morphisms are gauge transformations. And if G is finite, one advantage is that I don't need to distinguish between having connections or having flat connections. They are all the same. And now, just by trying to mimic the story we had before, I might want to say something like classical observables are functions on the space of fields. And then if I look at this groupoid of G bundles, there are two things I might mean by this. I could just mean like functions on the isomorphism classes of principal bundles, or I could mean something slightly more derived, where I take normalized cochains with values in C. But since G is finite and we are in characteristic 0, these two things are actually quasi-isomorphic. So the map from, there's a map from here to there, which induces a quasi-isomorphism. So there's not much happening. And now we can directly see that this will not form a factorization algebra. Because if I look at this on like on a one-dimensional disk, I will just get a point. Or on any disk, like pi 0, there's only one flat bundle on a disk. So I will get a point. But if I look at something like S1, then I will find the class functions on G. And I will not be able to build this by locally gluing together disks. So somehow there's like some type of conflict between having functions on moduli spaces and observables being a factorization algebra. And what I try to argue is that maybe the problem is more with the functions than the factorization algebras. Now let me, so this was somehow a warm up for the example we're actually interested in, namely the moduli space of flat bundles. So sigma is some surface, and G is a compact semi-simple Lie group, or if there's something more algebraic, then it should be a reductive algebraic group. And we can now define the moduli stack of G bundles on sigma, where the objects are flat G bundles, and the morphisms are gauge transformations. And as a concrete description, these are given by their holonomy. So group homomorphisms from the fundamental group of the surface to G. And now the gauge transformations act by conjugation on these group homomorphisms. And furthermore, if we have a surface sigma, which has at least one boundary, then the fundamental group will be free on 2G plus K minus 1 generators. So the group homomorphisms are actually just 2G plus K minus 1 copies of G, and then G acts on this by simultaneous conjugation. And this is also the phase space of 3D Schoen-Simon series, so we expect it to have a symplectic form. And this actually already goes back to work of Attia and Bott, where they define a symplectic form in the following sense. So like a tangent vector to the space of connections is a one form with values in the adjoint bundle. So if I have two such one forms, I can define a pairing by wedging them together and integrating over the surface sigma. And here we use like some normalization of the killing form to actually produce something we can integrate. And then this descends to a proper symplectic structure on the moduli space of G bundles. And a more modern way of defining the same symplectic structure is the following. We can note that it's known that BG is two-shifted symplectic, and then the AKS deconstruction via transgression defines a zero-shifted symplectic structure on the mapping space from sigma into BG. And this is exactly flat bundles on sigma. Okay. And now what happens if sigma has a boundary? Then it's not symplectic anymore, but there's still a Poisson structure. And a concrete description of this has been given by Fogg and Worsley, where they do the following thing. They define a Poisson structure on this larger space. based on a classical R matrix, so that this classical R matrix also defines a Poisson Lie structure on G, and the Poisson structure here is so that the action becomes a Poisson map. And then there's a recent result by Pavel Safronov, which tells us that this type of information is the same as giving a Poisson structure on the quotient stack. Or another way of getting the same Poisson structure as the following. We can note that essentially via the AKS Lie construction again, and by fixing one boundary condition, I have a restriction map from flat bundles on sigma to flat bundles on this boundary. The boundary is G, is the quotient stack of G where G acts on itself by conjugation. AKS Lie tells us this is one shifted symplectic, and this map actually becomes Lagrangian. Is this true? I think so. Maybe I should have taken all boundary components here. Yeah, probably these should be all boundary components. Anyway, but then the restriction to the boundary becomes Lagrangian. And in derived algebraic geometry, I mean, always Lagrangians give like somehow a specific example of co-isotropic structures for the corresponding Poisson structures, and then a co-isotropic structure in the derived setting. If this is one shifted Poisson, then this needs to be zero shifted Poisson. Or said differently, there's a symplectic structure here, and the Lagrangian structure needs to give us a trivialization of the pullback of the symplectic structure to whatever we have here, and this trivialization will induce a Poisson structure. Okay, not, but to me it's not clear if this actually exactly gives the Fock-Rossby Poisson structure or something else. And now, so what one would probably expect now is that like the quantum theory should somehow in these settings be a deformation of these Poisson structures on stacks, and there's a theory. No, there are actually two theories for deformation quantizations of stacks, but they are not directly related to deformations of algebras of functions or something like that. So they more work via like picking, I mean, especially this approach, picks by resolution through things which can be described by commutative differential graded algebras, and then quantizations of those. But the solution here, or the solution I want to propose, which that will not work in general, but seems to work reasonably well in the setting where the stacks showing up are mild, and maybe it should work if one replaces, if one thinks the story to the end is to do the following. We take functions on the space of solutions to something like higher functions on the space of solutions, so something like vector bundles or quasi-coherent sheaves. And let me just briefly recall what a quasi-coherent sheaf is. So if M is some affine algebraic variety, then the category of quasi-coherent sheaves are just the modules over the algebra functions. And in there we have the perfect modules, which are the finitely generated projective ones, and they correspond to dualizing objects, and they are what differential geometry one would think of vector bundles, so something like the Seswan theory. And then if we are in the setting, we have a quotient stack. I can look at the algebra of functions on M, which is now comes with an action of G, so it's a representation of G. So I can look at modules over this algebra, but within the category of G representation. So I can look at equivariant modules, and then this is the category of quasi-coherent sheaves on this quotient stack. And more generally, and also including this example, one defines it via taking this definition and right-can extending it to other stacks. And then the category of the category of quasi-coherent sheaves It's also symmetric monoidal, where the tensor product is given by tensoring over OM. Okay, now let me state a theorem in this context, which goes back to the work of Ben-Zvi, Bochet, and Jordan, which show that the category of quasi-Coherent sheaves actually form a factorization algebra with values in symmetric monoidal, locally finitely presentable categories. And this their result only holds if there's at least one puncture or boundary. And why is this? Why should you at least expect that quasi-coherent sheaves do better than functions? The reason is that if I look at a disk, I find that quasi-coherent sheaves on a point mod quotient stack by G. And these are representations for G or modules for the enveloping algebra. And then this is not what they exactly show. What they show is that the category of quasi-coherent sheaves is given by taking factorization homology of web G over sigma. And I will hopefully have time to say more about factorization algebra later, but essentially by construction, this will define a locally constant factorization algebra. So this shows that this is a locally constant factorization algebra, and now we can, like, there's a good guess on what the quantization of this should be. Namely, we take this the representations of G and replace it with the representations of the quantum group at some value Q, which should not be a root of unity normally. And then what they did is they used this as a proposal and computed some of its values and showed by direct computations that from this one gets quantizations of, for example, the Fock-Bostic Cosmos structure. Here are a few things which were not so clear to me. First of all, like, in what way is this a deformation of this? So what do we mean by deformation? Then how do we see Poisson structures on the categories of quasi-coherent sheaves? Right, and for functions on a moduli space, it's reasonably clear that we, like, how a Poisson structure exactly defines something on there. And then, like, why should we even expect that this is a good thing? Why does, like, computing factorization homology is compatible with quantization? So this might go under the name like local to global quantization, where we quantize something locally and then get a global quantization. And the last thing, which might be a bit minor, but for certain applications it's definitely relevant, is that what's the formal version? So this is somehow for complex parameter Q, but there's also a formal version. And then there are situations where we don't have, like, rational deformations, but only the formal ones. And then this should also be clear. And so the following will be some suggested answers to some of these questions. They are definitely not perfect, and there are a lot of things missing. And I should also say, some of the setting we work in is more the one of perfect sheaves or not complete categories. So we work in ordinary linear categories and not in these locally finite presentable categories. However, it should be possible to map there via an appropriate way of taking something like completions, like completing under all colimits or something like that, or enriched colimits here. Okay, so this ends my slightly long introduction, and I will now start giving some definitions, but first, it's probably a good time to stop for questions. So if you have any questions, let me know.
Can I maybe, it's maybe a remark more than a question, but 3 slides ago, can you hear me? 3 slides ago, you said solution colon, and then replace functions with, no, further one in the right, So it says solution, replace functions with higher functions. I think what you mean here is, this is like a proposal for how to proceed, because there's certainly other things one could do here, right? So this is not this, or maybe it is, depending on. So one thing that comes to mind here, specifically as you amplify restricting to perf, is that you could go to, instead of just mapping to vector, to the stack of vector bundles, you could map to the K-theory. Consider K-theory classes, right? And that would, one slide further down the road, give you the representation ring. Instead of, I think you just get the representation category, right? When on the next slide.
Yeah.
Or maybe on this slide.
I mean here, yeah.
Then, yeah. Yeah, anyway, so that was just a remark. You're making a choice here, right? Which now takes you down a particular road.
Also, like I should have made this clear, I don't think it's the best solution. It's something which works for the problem at hand. So this is probably what one should do. It's just practically quite complicated. And then even like this will, imagine having something like a higher gauge theory. This will still not CC enough. There you should do something like NVect or so, right? You should just, I mean, probably just take like as high functions as you need or something like that, right? It's somehow we are in the good setting where quasi-coherent sheaves see a lot about the stacks we are interested in, which is not necessarily the case. But yeah, I should not say this is the solution. This is like an ansatz of what we try to, what we use and what seems to at least allow us to get to some practical applications and also do concrete computations. But no, I definitely didn't want to say this is the only approach, right? There are a lot of other approaches one could take. There are probably a bunch of things which are better motivated than what's happening here.
Can I also ask a question? So physically, how do we think about this replacement? We know what it means to have functions on the solution space into it. We know physically what it means, right? So now we replace the target with some category. So what does that mean? Like
that's I would say I'm not completely sure, but like this looks something to me a bit like something like line operators, right? If you have a representation, you can form a Wilson line operator associated to it. So it's somehow slightly less local. You could also just from like categorification ideas, you might think if you can go one level up in categories, you will go from something like point defects or things which are local to things which are localized on lines. This is one interpretation, I think. Also, these things in a four-dimensional Yang-Mills theory, these form like boundary conditions or branes on certain twists, I think. But I should say I don't have like a good answer. So.
That's good. Thank you.
But I mean, I think maybe one other thing is, right, the thing we are at least classically interested is the space of solutions. And if you want to look at it, I think it's easy to see, or like it's by now probably people are comfortable with the idea that this is not a manifold, but it's more like a higher stack or some object in higher geometry. So it has inherent higher geometric features, and then functions on it might just not be sensible to these things, right? So as we go back even further, functions on here, somehow they only see the isomorphism classes. They don't see any of the higher geometric information. So if you want to have something which is more sensitive to these higher geometric functions, one way is to use like these categorifications of function. I would say. I mean, nothing I think is a perfect answer, but these are all, somehow like maybe some motivations to consider these things. Okay, let me move on. I should say that this is now, if you got lost before, this is a good time to start listening again, because it's, I will start with something slightly new. So let me first recall what a deformation quantization of an ordinary Poisson algebra is. So I fix some C-linear Poisson algebra, and then a deformation quantization is an algebra A, which is over it's a module over formal power series in H bar. And I want that it looks like formal power series in the original A, essentially. And then it has some deformed multiplication, which usually is called a star product. And then I want that if I take A H bar, if I set H bar to be 0, so I divide out by this ideal, I get the original algebra A. I get the original algebra A as a commutative algebra. Meaning, if I look at the commutator, this must be divisible by H bar, because here everything commutes. So I can divide by H bar. And then we say it's a deformation quantization of this commutator reproduces the Poisson bracket modulo H bar. And let me just give a slightly different perspective on this, is that the Poisson bracket can be used to deform the multiplication on A, where I add the formal variable epsilon. And then I just add epsilon times the Poisson bracket here. And for this to be a first order deformation, I don't need to satisfy the Jacobi identity, I just need the Laplace identity. And then if I can ask for, I can look at this deformation and I can tensor it with C epsilon over C H bar. So this is somehow looking at the, just saying H bar squares to 0. And then I can ask this to be isomorphic to A epsilon. And if this is the case, then it definitely induces 1. And in good cases, also, if I have 1, I can conclude that there is an isomorphism like this, which works if there are no symmetric deformations. Otherwise, right, this would be a deformation which might have some symmetric part, which I will not see here. And like good means, for example, if A is smooth. So let me just recast what I said. It's like somehow we can think of Poisson structure as defining a first order deformation, and then the quantization extends this first order deformation to a formal deformation. And the Jacobi identity shows up as an obstruction to extending this to the formal variable which squares to 3. And so the perspective which is easier to categorify is the following, namely Poisson, like what we really want to look at are first order deformations, and then their deformations extension to formal deformation. And somehow the reason we have the Jacobi identity is that this is the easiest obstruction to finding quantizations. So and then what this leads to is what we call an almost Poisson algebra, which essentially one could probably also call it just the first order deformation. So if I have a commutative algebra, I can forget that it's commutative and look at an algebra. And then I can look at an algebra which is a module in the category of modules over C epsilon. And I can set epsilon to be 0 to get a map here. And an almost P1 algebra is just an element in this pullback. So it's a first order deformation of a commutative algebra. And then an almost BD1 algebra is a first order, it's a formal deformation of a commutative algebra. So we again formulate it as this pullback, and then tensoring with the epsilon over a formal power series gives me a functor from, this is the wrong way, sorry. Gives me a functor from almost BD algebras to almost Poisson algebras. And the quantization of something in here is just an element in the free image of this functor or the homotopy fiber. So it's some formal, it's like, right, it's an algebra in formal power series, which reduces to the commutative algebra modulo H bar. And the first order deformation is somehow controlled by this P1 structure. Okay, and now the advantage of this is this makes it easier to categorify. The problem is the PN operand is an operand in chain complexes, and categories are not naturally enriched over chain complexes, so it's hard to talk about PN algebras in categories. While this, it's easier to categorify. So let me just, this slide is mostly I hope, recollection. It's just if I take an associative algebra and want to categorify it, I end up with the notion of a linear monoidal category or monoidal category. So this is category C, which comes with a tensor product, a unit, and an associator. And the tensor product takes two elements in C and multiplies them. And then if I want to categorify a commutative algebra, I get something like a symmetric monoidal category, or maybe a braided monoidal category, because both of them can be seen as categorifications of a commutative algebra. And in a braided monoidal category, I have an isomorphism from X tensor Y to Y tensor X. So we replace the equality of X times Y being Y times X by having a specified isomorphism. And in a symmetric category, I require that this isomorphism, which is usually called a braiding, if I do it twice, I get the identity. So there's a trivial double braiding. And these things all have operatic descriptions in terms of categorical algebras over operands with values in topological spaces, namely these EN operands, which are given by embeddings of a bunch of disks into another disk, which are given by rescaling and translations. So the one operand, the operations are embeddings of one-dimensional disks into each other. For example, this here and this there would be operations. And then composition is just by composing embeddings. So I've drawn some compositions here. Then for E2, you would have like two-dimensional disks embedded into each other. And you see that there's a path in the space of embeddings, which just exchanges the two disks, which will give this braiding. And then there's a whole family which ends at like the E infinity operand, which is the same as the commutative operand, because infinite, like embeddings of infinite sphere, this will be contractible. And this is what corresponds to the thing here. And you also see this looks a lot like the pictures I have drawn when I talked about locally constant factorization algebras on R1. And it's actually true. There's a theorem that this extends. There's the theorem by Lurie that locally constant factorization algebras on Rn are the same as algebras over the En operand. And now we can extend the story to zero by just taking zero-dimensional disks sitting inside each other to points. And then there's only one operation in arity 0, one operation in arity 1, and no operations in all higher arities. So an E0 category is just a pointed category. Okay, and now this allows us to slightly extend and categorify the definitions we had here. So I take these diagrams and replace all of the pieces with their categorification. So, and I allow now EI versions. So I take EI algebras in the epsilon linear categories. This they can map to EI algebras in C linear categories. Here I have symmetric monoidal categories. I can forget the symmetric monoidal structure. And in almost Poisson I category is this pullback, and the same for BDI categories. Again, tensoring with the epsilon or setting H, requiring that H bar squares to 0. This induces a map which here also goes in the wrong direction. Sorry. And then something like an extension of a first order deformation to a formal deformation is called a quantization. Okay, let me give one property. So if I have, like for some example, in almost P0 algebra, then this is a pointed category. So there's a preferred element O epsilon. And if I look at its endomorphisms, this is an algebra in the epsilon linear category, so it defines an almost P1 algebra. And then if I quantize this P0 category to a BD0 category, I also get a quantization of this algebra to a BD1 algebra. This is just, this is somehow, also this one sees here that there's a shift by 1 when passing to categories. And then the easiest example is just you take a commutative algebra category with one object, and this is automorphisms, and then a P0 category is the same as a P1 algebra, and a BD0 category is the same as the deformation of that. Then if you just take an arbitrary category, deformations are encoded by Hochschild code chains, right? So you can just write this composition as like the original composition plus like a deformed thing, which is a map which takes as an input F and G and gives a map from, let's say this goes from A to B and this goes from B to C, then this gives a map from this needs to be a map from A to C. And one can check that this is exactly Hochschild cosine, and then an extension just maps this to a formal thing. Okay, here are some examples of almost P1 categories. I will probably skip that just because I'm a bit slower than I thought. But one thing to keep in mind is something like functions on a Poisson-Lie algebra. Taking modules for that gives an example, and also modules over deformations of enveloping algebras. Okay, and then I think I will need that later. So let me give you an example of a almost P2 category. For this, we fix some classical R matrix on G, and then we look at modules for the universal enveloping algebra, and we just linearize the Hom spaces. So we just add a formal parameter, but do not deform the composition. For the tensor product, the only thing we deform is the braiding. For this, we use the old braiding, which was a flip, and then we put in an epsilon and act with the symmetric part of the classical matrix. And this defines a P2 deformation. And this is just a specific example of what's known as an infinitesimal braided category. And another example is like the epsilon version of the formal quantum group, where we leave the product the same and we deform the co-product by taking the commutator with the R matrix, and then modules over this also define a P2 deformation, where I change the braiding via an action of an R matrix. Okay, now both of these things have extensions to formal deformations, going back to the work of Greenfeld. So there's on the one side, there's a Greenfeld category, which is just we take UG modules and add the formal parameter H bar. And then the braiding, the braiding is just the swap plus now e to the H bar over 2 times the symmetric part of the R matrix. And then to make this into a monoidal, braided monoidal category, actually, one needs to use a non-trivial associator, which goes sometimes using what's called the Greenfeld associator. So this is like somehow, this is now a complicated power series in H bar. And this is a quantization of this Poisson structure. And I can also look at modules over the formal quantum group, which if I send H bar to be 0 induces this. And Greenfeld has shown that these two things are actually equivalent by what's sometimes called a twist equivalence. Like okay, this is also important. Like I'm trying to skip some things so I can stay on time. Sorry about that. But so here there's just an additivity statement which tells us if we look at EJ algebras in almost PI algebra categories or almost BDI categories, then this is the same as almost BDI plus J or P plus J categories. And these equivalences are actually compatible with taking the H bar goes to 0 limit. And the easy way of proving this is the following: for if I want to look at an EJ algebra in something, this is the same as giving a symmetric monoidal functor from the frame this category in dimension J into this something. So if I give a map into a pullback, I can use the universal property of pullback to also describe it as maps into the individual pieces. And then there it's just done additivity for EI algebras. Yeah, and this is, I should also say, this is a good argument, making it precise in a bicategorical setting we are working in here is actually quite involved, and it seems to us easier to just check it by hand. But somehow the proof by hand is not as nice to present. Okay. And now the last bit actually discusses how these concepts interact with factorization homology. Let me give a really brief recall on what this is. So we denote by man2 the topological category or infinity category of oriented two-dimensional manifolds where morphisms are given by embeddings. And it's symmetric monoidal with respect to disjoint union. And then we take the full subcategory on manifolds which are disjoint unions of R2, so they are two-dimensional disks. Then the input for factorization algebra with values in some target T is a functor from this disk category to T. And in 2 dimensions, this is the same as giving what's called a friendly 2 algebra in T. And then there's an inclusion here into manifolds. And factorization homology is defined as the left-Carnot extension of A along this inclusion. And given that the target is nice enough, this can be computed by a co-limit formula. So this is a co-limit over all disks sitting in sigma, and then I evaluate A on these disks. So in a certain sense, this is like integrating A over the manifold sigma. Yeah, and it goes back to, this formulation goes back to Ayala and Francis, and then there is also slightly similar, slightly different formulation by Louis. And then how does this relate to factorization algebra? There's a statement which I found somewhere in Ayala Francis that if I compute this factorization algebra homology, I get a locally constant factorization algebra on whatever I computed. And also actually factorization homology induces an equivalence between certain disk algebras and locally constant factorization algebras on M. Okay, this is not important for what follows, so let me not say too much, but it's actually possible to characterize the image of functors here explicitly. These are the functors which satisfy the local to global property. So this is a functor F such that I can reconstruct it by restricting to this and then doing factorization homology. I call a functor local to global if this is an equivalence, and Ayala Francis calls them homology series and show that this property is actually equivalent to them satisfying what's called tensor excision. Okay. Now coming back to the thing we started with, we want to define almost P0 structures on the factorization homology of modules for the universal enveloping algebra, because we know if we complete this, then we get quasi-coherent sheaves on the flat bundles, and in particular the endomorphisms of this pointed object in here, exactly the functions on the moduli space of flat bundles. And now we want them to somehow have this local to global property. So I want to understand functors like this from 2-dimensional manifolds to P0 category. And what I discussed so far is that factorization homology gives an equivalence to disk 2 algebras in here categories or here P0 categories. This is again the epsilon equals 0 limit. And then the Poisson additivity, this additivity that I showed tells us that this is the same as giving a framed almost P2 category, which deforms this framed E2 category. So if I want to define Poisson structures here, I can look at deformations here. And we have seen 2 examples which actually emit a framing. So I get 2 different almost P0 structures on this category, but they're also equivalent because the result by Greenfeld tells us that the inputs are equivalent. Okay, and then one thing one can check is that the Poisson structure one gets on the functions on the moduli space of lab bandit actually agrees with the one of a defined by a T input. And in the setting there is a boundary. We can do even more because there we can look at what's called the internal gain algebra. So if there's at least one boundary, I can fix some marked interval. And then I get an action of A, which is what the factorization homology assigns to a disk, onto the factorization homology on this larger manifold by mapping this the disk close to the boundary and then using the map induced by this embedding. This is the action. And I can also look at the map P, which just goes from A to this to the factorization homology, which is just inserting the pointing here, which is like, or I can look at the embedding where I have the empty set here. This also embeds here, and then I get a map P like this. And now we can define what is called the internal gain algebra, which is a functor from A op to C epsilon modules and ascends an element A to the space of morphisms of P of A into this pointing, which comes from the embedding of the algebra of the empty set. And since this map is an action, this whole thing will be Lax monoidal, meaning it defines an algebra object in three sheaves. On it, meaning an algebra object in the completion. And then you can ask, what is this algebra object? And these two things are now more expectations and propositions. So first of all, it's they are deformations of functions on G to the 2G plus K minus 1 together with the G action. And actually both of them are known functions. One gives rise to this Fock-Rossley Poisson structure I've mentioned before, and the other one gives rise to not a Poisson structure, but a quasi-Poisson structure, which has been introduced by Alexeyev and collaborators. And then these two things actually turn out to be formally equivalent just because the inputs are equivalent. And this would reproduce a certain well-known twist equivalence in Poisson geometry. And now the next thing is that this is actually the whole diagram is compatible with quantization. So we have framed almost PD algebras. There's some, okay, this should not have an integral. This is equivalent to this two algebras in almost BD0 categories. Factorization homology gives an equivalence here. So if I want to study a deformation of this sheaf of Poisson categories into a sheaf or a functor locally, something which is local from manifolds to BD0 categories, I can equivalently look at the deformation of this frame P2 category into a frame BD2 category. And this is exactly what the Greenfeld category and the formal quantum loop do for us. So they actually provide quantizations here. And then just using the commutativity of this diagram, we will find quantizations here. So we will in particular get for free essentially quantizations of the factorization homology for UG mod and leading to deformations of algebras of functions. So one thing is that automatically we get a quantization of the idea about Poisson structure on the functions, but then also looking at internal and these internal gain algebras, we get quantizations of the equivariant quantizations of the Fock-Rossley Poisson structure, and we get quantizations of the quasi-Poisson structure to an algebra now in this Greenfeld category, which should be the quantizations constructed by Lee, Blunt, and Chevera. And it actually has not been known, or at least not written down, how these two things are related. But now somehow formally it follows that they're equivalent from our work. Okay, and I think I will stop here and not say anything about how to actually compute factorization homology in these settings. So yeah, thank you for your attention.
Any questions for Lukas? So I have a question. In the beginning, very beginning, you looked at the spaces of the form sigma cross R sub t. Very simple question. So is that R or R plus? Are you considering negative time, or is it really
also negative time? Yeah, just the real.
negative?
Yeah. Otherwise, you can also do like, I mean, if you like topologically doing time larger than 0 or all times doesn't matter, but if there's a boundary, then you would also need to give a boundary condition, which, where is it? In this setting here would be the same as giving a left module over the algebra. So then,
I see.
Then we should give like wait, let's say here we should give like a P0, P1 algebra, but we should also give a P0 algebra of P0 algebra for somehow associated to the boundary, and this should have like a compatible action of the P1 algebra.
Sounds good. Thank you. Well, one other thing, you mentioned that factorization algebra is pre-factorization algebra plus some descent for Weiscover. What is the latter?
Yeah, sure. So, I mean, one thing what you want for factorization algebra is that if you take two disjoint unions, then somehow you assign to it the tensor product. And this will not be compatible with descent for all open sets, because if you would have descent for all covers, this should be a product or a co-product. So a Weiss cover is just a cover. So it's a cover UI, I, which has the following property. If I have a finite set, so if I have a finite set of points in M, then this must be contained in some of the UIs. So for any finite set, there must be a UI containing all of the finite sets. So how should you think about, or one way of getting a Weiss? Okay, so here's a way of thinking about a Weiss cover. A Weiss cover is a cover on M, which gives you a cover on the Rahn space, where the Rahn space is like the space of configurations in M. So it's like all different type of points you can have in M. This means, and the other thing of building a Weiss cover is you just start with like some cover given by small open balls. This is not good, but then you just add all the finite disjoint units. So I add these two things, and then I add 3 balls and so on. And if you have seen like embedding calculus, there are also similar ideas shown. So it's really somehow on the physics side, what I think this corresponds to is saying that somehow knowing the correlation functions, which are like observables for point insertions, for multiple point insertion. So there's something like this, or maybe these disks somehow fixes the theory completely. This is what one way of maybe motivating Weiss descent.
Oh, I see. It has to do with the trivertex governing everything. You mentioned 3 as an example, or 3 explicitly?
It's an example. I mean, yeah, no, it can go on. You need to go up to higher things as well, right? I mean, you need to take, because here you want it for all n. So if I take all disjoint unions, or if I take unions of n things in my cover, then I will get then all endpoints will be in there.
I see. Yeah.
And I mean, you can but you somehow maybe hope that, I mean, so I should say wise descent is weaker than normal descent. And you can truncate this at any n if you want. So I could like ask this for only sets of size 3 or so. And then I would get a different type of descent condition. And so there's like somehow a tower of descents, and this is somehow the strongest one, meaning that all endpoints functions. Maybe if you say something like three points are enough, then somehow 3-point functions would fix the theory. But this I should also say like as a bit like informal. This might be completely wrong and doesn't match the physics at all.
No, that's very interesting. Yeah, thank you. Any other questions, comments?
Can I ask you a question to maybe clarify on the big theorem you showed with the big commuting diagram? There was a whole lot of notation and concepts there. I think I lost track a bit. I was wondering if I could ask you to sort of say in words what the upshot is that we're proving.
Okay.
So yeah, here this diagram, right?
Exactly. So what, right? Like what we look at is, I mean, let's say first functors local functors from manifolds to categories. So what we think of here
so
is
this
like,
I should think of. That's like a classical field theory, even without
yeah, exactly.
structure now.
This should be a classical field theory without Poisson structure, but it somehow it has like a local property.
Sorry.
This is something like.
I guess the upshot is that the right-hand side of the diagram is complicated or looks complicated, right? To have these, yeah. So we want to lift up to maybe classical field theories and then quantize as field theories. And if I understand well, the point is that as we go to the left, we have a chance to actually do the deformation explicitly, and then know that it exists on the right.
Exactly, and compute it on the right. So here, for example, I want to do somehow. I mean, I think the upshot is the following: like, assume you have a theory, which, like a classical theory, which is somehow defined on all two-dimensional manifolds and local in the sense that you can glue fields and you can glue solutions, and so on. So if it's local, you could try to construct a quantization in the following way. Look at what happens on a disk, which is usually an easier problem, and study a quantization there, and then glue these things back together. And the theorem tells you that this is not exactly enough. You can look at quantizations at a disk, but you should also quantize the structure on how all the disks sit inside each other, right? This means that these are like disks sitting in here, like this somehow studies these two algebras somehow study the same problem you had on disks, but also in the ways they can sit into each other. And then if you quantize there, this is good enough. And then the other statement is that instead of studying the values on all these different disks, there's like a different structure, which is like a braided deformation. And we can look at one quantization of this, but as a braided category. So somehow deforming a field theory on two-dimensional manifolds, which is really nice. It's the same as taking an E2 category and looking at taking something like a symmetric monoid category and deforming it as an E2 category. And then factorization homology will somehow take these two EN directions and turn them into two space-time directions. And yeah, the statement is that this is something which is actually like doable, and then somehow you get all the other things for free, and you get them formally. I mean, can maybe say some of the applications is also that Now, if you find structures on here, which are like algebraic structures on here, running the machinery will give you certain geometric structures with Poisson structures and deformations. So for example, modules over the quantum group, there's an action of the outer automorphisms of G, and then there's an action of the two group given by B of the center, and both of them will give you Poisson structures on certain geometric objects. So for these out G actions, this factorization homology gives deformations of so-called twisted bundles, like by hand computations. This is something I worked out with Corina 2 years ago now. And so this would also follow formally. You can just like put in any type of algebraic structure and you should get some type of geometric structure. So there are things like quantum symmetric pairs, which should now give you something like a Poisson structure on certain orbifolds. And then they also, you can run this with defects and stratifications, and somehow just gives you a way of like reducing the quantization problem to something local in a way which ensures that you will or can like somehow glue these things back together to get a quantization. I mean, this is not a new idea, right? It has been like a lot of quantizations somehow do something local and then glue them back together. But here factorization homology seems to be a good framework in the locally constant setting to get these things for free. It's easier than something like combinatorial quantizations or something like that, where you glue, but then at the end you need to make sure that things are independent of your triangulation or something like that. And here, if one does computations, one quite often introduces certain combinatorial structures, but there's also the abstract algebraic structure, ensuring that the answer will be independent of all choices.
All right, thanks. Great. Any other questions? Okay, if not, let's thank Lukas for the very nice talk.
Yeah, thanks for the invitation.
Thank you, you all.